Good afternoon, everybody. Uh, so what I plan to do in next 30 odd minutes is give a very high level view of the landscape of AI, how it's progressing, and I would talk from chips to software to the models that IBM has been working on very actively. So if you look, so AI is not new, right? People have been trying to build these AI systems for last many decades. The earliest such systems were built using what are called expert systems. And these expert systems are nothing but they are kind of rules, right? So somebody manually codes these rules, right? Like in this case, if power supply is on and if there is no red light and if you could no sound in the power supply, then you do this, right? So something of that sort is what people have been trying to build these AI systems. The earliest incarnation was a LISA system in 1960, which was a psychotherapist, which was built using this. Now, if you see this, this is actually very brittle and it uses no data. Somebody has to author all this. So it's very cumbersome, and people try to build this kind of system from 60s till 80s. After 80s, people moved on to these techniques called machine learning systems. They are of course less brittle and less labor intensive, but there is enormous amount of data that is required. So here is an example where you're trying to predict the price of a house based on a certain set of features. And some domain expert is going to tell that the house price is dependent on the number of rooms, the number of bedrooms, whether it has a balcony or not, the location of it, so on and so forth. So these are called features. Domain experts give these features, and then there are these machine learning models, and people have written several PhDs, and there are decades of work around creating these machine learning models, from logistic regression to SVM to decision tree to random forest. There are a bunch of such techniques where you use these data with these features that have been engineered and learn models. And this is what people have been doing since 1980 till 2010 or even later. And then we moved on to these things called deep learning. The model deep learning is also old, but we could train these deep learning models in effective manner only around 2010 or somewhere thereabout, because of the kind of processing requirements training of these systems need. So the deep learning model has an advantage over these earlier machine learning models, that there is no feature engineering that is required to do, right? So it can learn these features on their own. So that is the good part about these deep learning models. And after 2018, we moved to what are called foundation models, which are even better, which are built on top of these deep learning models. And good thing about foundation models is that you don't have to build different models for different problems. So with deep learning models, and the same is true with machine learning models, which were earlier, you need to build a different model for question answering, a different model for summarization, a different models for writing poems, a different models for everything, for a different task. With foundation model, which is what we see now in the form of ChatGPT, it's a single model which can do everything. So these are foundation models that people started to build 2018 onwards. So this is the journey of the way we have progressed from early days of building expert systems to these foundation models now. Now, as I said, the foundation model is a model which is built using billions of data points, and we'll see what we are doing there to learn these kind of models. But from that one model, you can get it for machine translation, for question answering, and for other kind of things. And the reason that it happens, how are these foundation models learned? They are learned by the huge amount of digital data that we have. There is so much of written data in English. There are billions of sentences. So the current day of these foundation models are learned using trillion words, trillion tokens, 15 trillion tokens. That kind of uses all the data that has ever been written digitally. They are using all that data to build these foundation models. And once you have built a foundation model, you need only a few examples, if at all, In fact, now you need no examples. You just need to instruct the model to behave in a particular way, which is what all the people here would have experienced with technologies like GPT and Llama and Granite models, where you can just say, do this, and it does that. Or you can give a couple of examples, and it does that. So that's how we have moved into these foundation models. But these foundation models are built using enormous amount of compute and enormous amount of data, ranging into hundreds of billions of sentences, trillions of tokens. That's what it takes to build these models. And I've already talked about that once you have these foundation models, you can do everything with them. Now, good thing about these models is that what we have seen with GPT-4 and Llama and Granite model, these are language models. That's why they are called large language models, because they are large and they are language model. They are modeling language. But it's not restricted to just modeling languages. In fact, you can model chemical compounds, you can model time series, you can, of course, model images and videos, and we see that as well in day-to-day experiences, but you could actually even model geospatial data. And that's something that IBM has been doing very actively. We have been building a lot of models in besides the language and images and video, also in time series and geospatial and other kind of molecular biology and those kind of things. The other thing that you need to build these foundation model is enormous amount of compute. And so IBM has these watsonx product portfolio where you have 3 pillars. watsonx.ai is a platform which enables training of these large foundation models. As I said, these large foundation model needs large amount of compute and large amount of data. So the data also needs to be stored somewhere, processed somewhere, and that's what watsonx.data does. watsonx.ai is for training these models. watsonx.data is for storing and processing this data. And watsonx.governance is for governing these models, right? So these models needs to be updated, and there is a lot of issues around the kind of data that you have used in building these foundation model, the licenses associated with that data. There is a lot of legal cases going on across the world on several companies for the license violations that are happening, which have been used in building these foundation models. So watsonx.governance is basically the product which enables you to find out which model has used what data, which have used what kind of licensing, and so on and so forth. So it allows you to governance that. So that's the watsonx platform that we have. Now, as I mentioned that language is only one part, right? So there are other kind of data that could also be used to create these foundation model. And I'm going to just spend a minute for each of these models that we have been working on. One of them is code model. So language we already saw. And in language, there is one important aspect about language though. So which is that everything that has been written has been used digitally, which is available, has been used in building these models. However, the enterprise data, which is proprietary data, has not been used. And in fact, these models which are available do not know about some company-specific information, some enterprise-specific data, which is proprietary in nature. So a very small amount of such enterprise data is actually available. What we can do using this watsonx platform is to take these enterprise data and use that data to train models that are specific to that industry and that enterprise and that domain. So that is something that we can do, that we are actively doing using watsonx platform. So that's the thing on the language side, where we already have these models to start with, but we kind of need to incorporate the enterprise and proprietary data also into these language models, and that's something that we are actively doing. On the code side, of course, there is a lot of interest in trying to automate writing code, right? And there are different kind of tasks here, like, explain a code which is already written, or write a code given an instruction of that, or kind of debug that code, right? So these are different use cases that have been very actively used across companies now in their software development process. And IBM has been very actively building these models under Granite code model. And this chart shows a Granite code model comparison with other models which are also available, from Google's Code Llama to Meta's Llama to Mistral AI. These are different open source models available for code. and Granite model, which is for the same size. So one of the other thing about these models is that these models' performance improve if the number of parameters, and the number of parameters is nothing but it's kind of a quantification of how large a model is. Larger a model is, better it is. But more compute is required to train it, and more compute is required to inference, which basically means for using it. So what we are looking for is models which are not as large, like they are not running into trillions of parameters or hundreds of billions of parameters, but much smaller, but with much more strength. So these are like 8 billion parameter model, and Granite model is actually performs very fairly across many other open source models that are available for all these code related tasks, from explaining a code to fixing a code and from generating code. And Granite code is also very transparent, right? There is a growing concern in the kind of data that has been used to build these foundation model, whether the data is open, whether these models clearly explain the data that has been used to build them, and whether whatever they are generating, there is an explanation of why the output has been generated. So to capture those kind of things, Stanford has come up with these transparency index, and IBM Granite model fare very, very positively, as you can see here, compared to many other models which are coming from enterprises and are also open source. So that's about the code model. Time series model. So just like language model are modeling language, code models are kind of modeling code, the time series models are trying to model how the time series kind of would unfold as time progresses, right? So like you are given a graph which is being shown that as time progresses, it's progressing like this, and you are trying to learn these machine learning models or deep learning models, or more specifically what are called transformer models. These are kind of deep learning models, and now you want to forecast that how this time series is going to go forward, right? That's what we are trying to do as part of these learning of time series models. And they have very enormous amount of application, right, for weather forecasting, electricity demand forecasting. In fact, in case of telecom, there are so many problems that can be modeled as time series prediction problem, like network optimization problem, resource allocation problem, anomaly detection. All these problems can be modeled as time series prediction problems. And IBM has been doing very, very extraordinarily good on building time series model and putting them open source. Very latest, we have open source this model called Granite time series model, tiny time mixers. It's a very, very small model. And that's what this chart shows. This chart shows on the left chart, you see that there are these other models which are all built for modeling time series, which are 709% larger than the rightmost that you can see. It doesn't even, you can't even see, it's just a blip. Granite time series, TTM model. And Llama is 2.4% larger, GPT-4 for time series is 84% larger, and the largest one is 709% larger. So that's how small this Granite tiny time mixer model is. But at the other hand, if you look at the performance, and these are errors, so smaller is better, and the blue bar here is what the tiny time mixer's performance is. And you can see under different conditions, it has the lowest error compared to other models which are much larger in their size. And this is a very, very widely followed work and very, very widely used model. It has already been downloaded for more than 1 million number of times and very actively being used for many, many applications. And I think it draws particular attention for a telecom audience, because there are so many problems in telecom domain that can be modeled in time series, and we have very good time series models which are small and are very, very performant. And there are many, many news articles around this, around Granite tiny time mixers, TTM models. Coming to the geospatial model, there is a lot of satellite imagery that is available across multiple years. There are Landsat satellite which has been in operations for decades. Similarly, Sentinel 1 and 2 are other satellites. So there is a lot of radio imaging data set, satellite data that is available through NASA, and IBM has a great partnership with NASA where IBM has used this data called HLS data, which is harmonized Landsat and Sentinel data, which is basically this all radio imaging data, and then have learned a foundation model, a base model, right? A foundation model for geospatial data. And once you have that geospatial foundation model data, we can actually replicate the same story what we have for language, where we have one language model, and with very little or no data, it can be now used to summarize, to machine translate, to any task. So similarly, once we have this geospatial foundation model data that we have built along with partnership with NASA, with very little data now we can use this model for flood detection, for wildfire scan detection, and for biomass quantification, for many applications in agriculture, because all these applications require a lot of fine tuning, a lot of data. But now with this foundation model, the requirement of this additional data is very, very minimal. So that's what we are doing, where we have taken the geospatial model, and this is basically showing how foundation models are learned, right? So these foundation models, these large models are learned from data which is not labeled. So these are being learned from images and then randomly blocking certain portion of images and then trying to predict those images, right? So that's how these foundation, this is called masked language model or masked geospatial model, where we are trying to, so given the image on the left side where you see certain black squares, so that's kind of being blocked from the input image, and you want to predict the right image which has the actual image. So that's how, you know, we build this geospatial foundation model by solving this problem across years of geospatial data that is available. Please note, it is not a labeled data, it's just data. And that's what is being used to create this foundation model. And once you have that, then you use that geospatial data and very little data that is available for fire scan detection, which will be, here is how an image where, and here is the portion which has the fire, or here is the portion which has the flood. But you need very, very little data like that now to build flood detection model and so on and so forth. So that's what IBM has been doing along with partnership with NASA, and this Granite geospatial model is also open source, which is available for people to use. Finally, I will also talk very briefly about the hardware side of things. So if you look at the progress, there is a tremendous progress that has been made. But that progress has been made with CPUs, the central processing unit, and GPUs, which are graphical processing unit. Now these hardware are excellent. They're very flexible. You can use them to build whatever you want to build. So they're very flexible, and then they're very precise. The mathematical computation that is done by CPU and GPU is very, very precise. However, it's like, you know, you're trying to use a diesel car with a petrol fuel or something like that. Like CPU and GPU have been built for something which is very flexible and mathematically very accurate. Now for learning these deep learning models, you don't need to be that precise in your mathematical computation. And that's where we can use different kind of hardware architectures to train them and to inference them. And that's what the intent is for IBM. IBM Research had launched a IBM Hardware Accelerator Lab in 2019 in New York, which is building these chips, which are very specific for learning these AI models and for inferencing them. And you know, we have this approximate computing. As I mentioned, for deep learning models, you don't need that precise mathematical computation. You could work with lesser floating points. You don't need 32-bit representations, but much lesser, and therefore you can reduce the amount of memory and time that is required and energy that is required to train these models. And that's what we are doing with building this artificial intelligence unit, AIU. And it also has a very simplified architecture which is more optimized for the kind of operations like matrix multiplication and vector computation that is required for training these models. There is also this other work that we have called North Pole, which is brain inspired. And if you look at the figure on the left hand side, on the right hand side here, the red blocks are the computing blocks, CPU blocks, and the blue blocks are the memory blocks. And that's the typical von Neumann architecture for computing that has been going on for decades. We have a memory separate than the computing. And that is not how brain works. In brain, computing and memory both are imbibed in the same neuron. So they live very nearby. But all our computing architecture today has this separation, and that creates what is known as von Neumann bottleneck. Right, so because this memory needs to, all the data needs to be transferred from memory to compute, and that creates a lot of bottleneck. So we are looking at these newer architecture called North Pole, and that's on the most right side, where you will see that red and blue are mixed. So compute and memory are kind of mixed together. And that creates a lot of efficiency, and North Pole is way, way high in terms of x-axis is defining how many frames per joule, and so it's basically is characterization of amount of space on silicon that is needed for a particular frame rate, as well as the amount of energy that is required to do that. And North Pole is way better. And it is specialized for inference, not for training. Finally, we have this whole work on AI Alliance. It's a big partnership across many, many players globally, including Meta and many other companies, many other universities. In India, we have recently partnered with IIT Madras, IIT Jodhpur, People Plus AI, AI for Bharat, Kisan AI, and basically these are the new partnership we have under AI Alliance, where our focus is to improve the AI skill and also to create tools which are more trusted, and also build on these hardware which I just talked about, also advocate the regulatory framework that are required for our AI models. So that's a work that we are doing along with many other partners globally as well as in India. So thank you for your attention, and please ask me any questions if you have. Thank you.